This is the third week of the Matemairacorana, and as our first speaker, we have José Laudelino de Menezes Neto from Federal University of Paraíba, who is going to speak on parametric stability of a pendulum orbiting the Earth. Laudelino, please.
Certo, então, em português mesmo, né? Pode ser. Pronto. Deixa eu tentar apresentar a tela aqui agora. E eu vou desabilitar minha câmera para ver se melhora também a apresentação.
Estamos vendo a apresentação, chegou.
Certo, eu vou desabilitar a minha câmera, que eu acho que melhora a minha conexão aqui também. Certo, então, eu vou falar da estabilidade paramétrica de um pêndulo em órbita na Terra, né, que é Parametric Stability of a Pendulum in Earth Orbit, né. Foi o trabalho que eu fiz com o Hildeberto durante a minha tese de doutorado, né, um dos trabalhos. E, a princípio, Hildeberto tinha dito para procurar algum trabalho que tivesse em órbita circular para passar para a órbita elíptica, né, para poder utilizar a teoria do Markov, que foi o que a gente estudou. Né? E na pesquisa, eu encontrei esse trabalho do Synge, de 1959, né, que ele estudou o comportamento de um pêndulo simples em uma órbita circular, né, da Terra. Só que ele fez as seguintes considerações, né? Ele considerou o comprimento do pêndulo fixo, que seria o normal. O pêndulo ele está preso num satélite, no caso pode ser a Lua, né? E ele considerou também o estudo nos três eixos, né? No eixo X, Y e Z, no modelo espacial, né? E usou um potencial aproximado. Ele pegou o potencial original e fez uma conversão para essa expressão aqui simplificada. Né? Então, no estudo dele, aí está uma figura, né, do estudo. Aqui está, nesse ponto O2, a gente seria a Lua, né, em órbita da Terra, onde fica no ponto O1. Né? O pêndulo aqui vai de O2 a P. Esse comprimento O2P é fixo, né? No ponto P, onde tem uma massa, né, e é feito o estudo do que ocorre nesse ponto P, nessa órbita, né, a estabilidade do pêndulo. Né? Então, o Synge, ele, ao fazer esse estudo, ele encontrou 6 posições de equilíbrio. Né? 2 no eixo X, 2 no eixo Y e 2 no eixo Z. Aí, dessas 6 posições de equilíbrio que ele encontrou, as do eixo X e Y foram instáveis, né? Ele até, aqui é a figura do trabalho dele, do Synge, ele botou a bolinha branca, né, para mostrar os equilíbrios instáveis, e ele encontrou 2 equilíbrios no eixo Z estáveis, né, e fez o estudo desses equilíbrios também. Então, a partir desse trabalho, né, seguindo a ideia de passar da órbita circular para elíptica, né, a gente fez a modificação para a órbita elíptica, né, desse trabalho, para poder fazer o estudo da gente, usando a teoria das curvas que tem no livro do Markov, que foi até mencionado na palestra de Cláudio Vidal. Então, a partir do trabalho de Synge, a gente passou de uma órbita circular para a órbita elíptica. Né? Só que aí, no nosso estudo, a gente considerou o potencial original, né, diferente do Synge, que fez uma simplificação, né, tornou mais simples, digamos assim. A gente, no meio dos estudos, a gente tentou primeiro usar o pêndulo com comprimento fixo, só que as contas estavam ficando bastante complicadas, né? Tentamos também, no início, usar os 3 eixos, né, X, Y e Z, fazer as contas no espaço, né? Só que também se mostrou bastante complicado para o prazo que a gente tinha para fazer essas contas. Então, nós colocamos primeiro no plano da órbita, né? Tiramos o eixo Y, ficou só no eixo XZ, que é o plano da órbita. durante as contas também, para tentar facilitar a minha vida, eu resolvi colocar o comprimento do pêndulo variável, né, de acordo com, digamos assim, o raio da elipse. Tem um parâmetro aqui de controle, que é esse beta. Então, o comprimento do pêndulo ele varia de acordo com o raio da elipse, digamos assim. A gente passou para o plano da órbita e primeiro a gente tentou fazer as contas também com coordenadas cartesianas, como o Synge fez, mas se mostrou complicado. E a gente resolveu passar para coordenadas polares, né? Que passou a ser, digamos assim, mais fácil trabalhar no momento. Também, pronto. Então, a gente fez essas modificações, obtemos as equações, né? Então, a gente obteve primeiro o lagrangiano do sistema, que eu chamei aqui de L, né? Mas eu não coloquei a equação do lagrangiano para não ficar muita informação. Então, só usando essa função lagrangiana, a gente passou, obteve as equações do movimento, né? Só na variável θ, né? Que só tem θ, em função do tempo t. Então, fizemos essas contas aqui. Então, ao fazer essas contas com lagrangiano, a gente chega nessa equação do movimento aqui, em função do θ ponto, né? Em função da derivada em relação ao tempo. Né? O raio, como é variável, né? Por causa de uma elipse, então o raio também tem derivada aqui. Né? Certo? Então, depois, a gente passou para o novo tempo ni, né? Que é a anomalia, né? Esqueci o nome agora que você fala, anomalia verdadeira. Passou passou do tempo t para o tempo ni, né? E obtemos essa equação aqui. Então, com essa equação, a gente obteve o hamiltoniano do sistema, né? Que representa esse movimento. Então, a partir da equação no tempo ni, a gente obteve a equação hamiltoniana do sistema, que está aqui embaixo, nessa parte do meio. E analisando esse hamiltoniano, e também dá para ver aqui pela equação em função de θ, né, no tempo ni aqui, dá para ver que tem dois equilíbrios, quando θ é igual a zero e quando θ é igual a π, né, que dá duas posições do pêndulo. E nessas condições, de acordo com o hamiltoniano, o pθ, que agora me fugiu o nome desse pθ, os dois valores dele são iguais a zero, né? Então a gente achou esses dois equilíbrios. E agora uma figura para mostrar os equilíbrios. Então a gente encontrou os dois equilíbrios e, de acordo com os valores de θ, né, para θ igual a zero e θ igual a π, esses dois equilíbrios estão no eixo Z, né, conforme aqui a figura. Tem a figura representando o equilíbrio E1 e a figura representando o equilíbrio E2. Então, quando θ é igual a zero, a gente tem a figura aqui no equilíbrio E1, que é quando o pêndulo está apontado para fora da Terra. Né? A Terra está aqui nesse ponto O1. E quando θ é igual a π, né, o pêndulo está apontado em direção à Terra, né? Está aqui nessa segunda figura. Então, a gente encontrou esses dois equilíbrios e fomos verificar se eles são estáveis e quais se dá para trabalhar com eles, né? Com a teoria que a gente utilizou. Então, a gente passou a trabalhar com os equilíbrios aqui, né? Então, obtivemos os hamiltonianos agora em cada equilíbrio, né? Na perturbação de cada equilíbrio. Temos aqui o hamiltoniano relacionado ao equilíbrio E1, esse aqui de cima, mais acima. O hamiltoniano relacionado ao equilíbrio E2, que está aqui embaixo, né? E a gente, para, digamos assim, evitar tanto trabalho, o valor do beta, ele teoricamente teria que ser só positivo, porque não existe o crescimento do pêndulo negativo, né? Mas a gente assumiu que ele pode ser positivo e negativo, seguindo um outro trabalho que também fez uma análise parecida. Então, a gente assumindo que o beta pode ser positivo ou negativo, basta trabalhar com algum dos dois hamiltonianos, porque a diferença de um para o outro são só esses sinais negativos que tem aqui nas equações. Onde tem esse menos 3 beta e esse menos beta. Então, optamos por trabalhar com esse hamiltoniano de cima, o H é 1. Então, ao trabalhar com esse hamiltoniano H é 1, né, o beta podendo ser negativo, de acordo com as restrições anteriores, o beta tem que ser maior do que menos 1. Né? E fazendo ainda mais simplificações, a gente chamou toda essa expressão aqui, em função, essa função aqui de beta, né, que é beta ao quadrado mais 3 beta mais 3, dividido por 1 mais beta ao cubo. A gente chamou isso tudo de um único parâmetro alfa. Então, a gente simplificou o nosso hamiltoniano H é 1 para esse H desenhado aqui em função de alfa. E, de acordo com a restrição do beta ser maior que menos 1, o alfa tem que ser maior do que 0. Aí, ainda nessa análise, a gente tem a restrição. Quando o alfa está entre 0 e 3, corresponde ao equilíbrio E1, que é o pêndulo apontado para fora da Terra. E quando o alfa é maior do que 3, corresponde ao equilíbrio E2, que é quando o pêndulo está apontado para a Terra. Então, a gente fez todas essas simplificações e arrumações aqui para, a partir desse hamiltoniano, aplicar a teoria para desenhar curvas, né, que vai separar as regiões de estabilidade e instabilidade desse pêndulo. Só que antes eu acho que eu esqueci. Usando esse hamiltoniano, a gente verificou que os equilíbrios E1 e E2 são instáveis, né, para poder aplicar a teoria. E a partir desse hamiltoniano, a gente, de fato, fez o que eu acabei de mencionar, construímos curvas que separam as regiões de estabilidade e instabilidade no plano dos parâmetros. Né? Alfa, que é relacionado ao comprimento do pêndulo, né, já que é relacionado ao valor de beta, e o Ezinho, que é a excentricidade da elipse, né, do plano da órbita, né, da elipse da órbita do problema. Então, usando esse hamiltoniano, é que a gente fez as curvas, né, que vai separar as regiões de estabilidade e instabilidade do problema. Né? Então, vou mostrar aqui as curvas. Né? Então, a gente, utilizando a teoria que está lá no livro do Marquez, o método de a priori e outros, calculando as ressonâncias e tudo mais, as ressonâncias estão indicadas aqui com as setas, né? Eu não sou muito bom em fazer figura. Então, a gente encontrou essas curvas. E entre cada curva dessa, que parte aqui de uma ressonância, é que você tem a instabilidade dentro dessas curvas aqui, né? Entre essas regiões. Então, no próximo slide tem uma figura melhor desenhada. Então, essas foram as curvas que a gente obteve. Até o alfa, como tem aqui na figura anterior. Até o alfa indo até 49/4. Né? Mas esse alfa pode se estender a valores maiores. Né? Só que, no momento, a gente só fez as contas até o 49/4. Então, aqui as curvas, uma definição melhor. E, depois que a gente fez todo esse estudo, eu não sei como, eu pesquisei muito para ver se outras pessoas tinham feito trabalho parecido, mas não tinha encontrado, eu só estava pesquisando por pêndulo, né, em órbita, orbital pêndulo e parametric stability, não estava encontrando nada. Aí eu não sei como, quando estava com o trabalho praticamente bem encaminhado, eu me deparei com um artigo que já tinha feito muita coisa parecida. Chega, foi um susto, e eu ainda lembro na época que falei para Hildeberto, a gente levou um susto, porque parecia que todo o trabalho tinha sido em vão, né? Então, a gente encontrou um artigo de 2012, esse trabalho que eu fiz foi mais ou menos em 2015, 2016, né, que é o de Burov, German e Kosenko, que já tinham estudado o mesmo problema, só que aí, por sorte, né, ainda bem, eles usaram outros métodos que eles mencionam lá, que é o método de Zhukovsky, eu não conheço, também não deu para ir pesquisar na época, e ainda bem que eles usaram outro método, né, porque sinal que não tinham feito usando o método que a gente usou. Pode até ver, eles chamavam isso de, em vez de pêndulo em órbita, eles chamavam de Moon Anchored Tether, né? Tether é ancorado na Lua. Então, Só depois é que eu vim conhecer que tem essa nomenclatura para pêndulo, que também pode ser teta. Então, eles fizeram um trabalho bem parecido, né? Inclusive, as simplificações que eu fiz no meu trabalho, eles também tinham feito no trabalho deles. E eles encontraram essa região aqui de estabilidade e instabilidade, né? A região de instabilidade está aqui em preto. Então, eu fui até comparar com o que eu tinha feito com essa região, para ver se era parecido. E fazendo o comparativo, né, aqui, eu rotacionei a figura para ficar de acordo com os eixos que eu fiz também, né, porque eles fizeram com outra forma de eixo, mas representando a mesma coisa, né? E eles, no trabalho deles, Burov, German e Kosenko, eles dizem que para alfa de 0 a 3, fora dessa região preta, você tem estabilidade, né? Só dentro da região preta que se tem instabilidade. E comparando de 0 até meio, a gente obteve curvas bem parecidas aqui, né? Não dá para comparar, porque eles não mostram analiticamente a curva, né? As funções, né? E aqui do lado a gente tem a figura que a gente fez de 0 mais à direita, a figura mais à direita, do alfa variando de 0 até 3. Né? Então, pelo que Burov, German e Kosenko falam, eles dizem que fora da região preta, você tem estabilidade, mas a gente encontrou outras regiões bem minúsculas aqui de instabilidade. Né? Então, o estudo que a gente fez foi mais refinado. Né? Então, de 0 até meio foi só até aqui que eles fizeram a figura, e daqui em diante a gente encontrou outras regiões e de instabilidade. Né? Aqui a figura do trabalho que eu fiz com o professor Hildeberto, né? A gente encontrou fora da região de 0 a 3, como eles dizem, fora desse pedaço, desse primeiro pedaço aqui, você tem estabilidade. A gente achou aqui duas curvas, né, que já mostra que tem uma região bem pequenininha de instabilidade. Então, se a pessoa, por azar, colocasse um satélite nessa região, ele possivelmente ia sair do lugar. Né? Então, está aqui. Essa figura aqui à direita é a ampliação dessas curvas aqui do lado esquerdo, né, de uma dessas curvas bem próxima. Então, entre essas duas curvas, azul e laranja, a gente tem instabilidade. Então, já foi um refinamento. E na parte do equilíbrio E2, né, no trabalho de Burov, German e Kosenko, eles dizem que para o alfa maior que 3, né, para o beta variando até 0,8, que eles fizeram um estudo para beta em vez do alfa, né, eles dizem que tem estabilidade, mas, de novo, a gente encontrou regiões bem pequenas de instabilidade. Né? Então, que está aqui nesse gráfico. Eles já disseram que quase não tem região com instabilidade, mas a gente encontrou regiões pequenas. Né? E Burov, German e Kosenko, eles chegam a mencionar que o método de Zukovsky não é tão aprimorado, assim, pelo que eu entendi. Né? Então, a gente encontrou, eles dizem que tem-se estabilidade nessa região aqui, né, que é de beta de 0 a 0,8 e o E de 0 a 0,9. Mas a gente encontrou, aqui está um comparativo do valor do alfa para o beta, que nesses valores aqui do beta, né, você tem algumas regiões, partindo desses valores, algumas curvas com uma instabilidade, apesar de ser bem pequeno, como mostra aqui na figura mais à direita, né, que entre essas duas curvas aqui, a azul e laranja, é um pedaço bem pequenininho, de 0,000 alguma coisa aí, você tem uma região bem pequena de instabilidade. Né? Então, se a pessoa tivesse o azar de colocar um satélite aí, provavelmente ele poderia sair voando, não sei. Né? Então, esse trabalho assustou a gente, porque eu não tinha encontrado na época, mas ainda bem que a gente conseguiu fazer por outro método, obtendo valores mais refinados. E quando a gente estudou, aí, por conta desse trabalho de Burov, a gente também encontrou ação para um pêndulo que estica no espaço, né? Que a princípio a gente achava isso absurdo, para que isso iria servir, né? E foi que a gente viu que há uma aplicação para um pêndulo de comprimento variável, até um pêndulo no espaço, principalmente de comprimento variável, que o pessoal vem estudando isso e acha interessante, né? tem até trabalho informando como fazer, que uma aplicação para esse tipo de estudo seria criar um elevador espacial, né, da Terra para a Lua, né, só que os custos para isso seriam muito altos, então tem umas figuras aí que eu encontrei na internet de algumas projeções de como seria um elevador da Terra para a Lua, né, só que mesmo que não seja possível fazer um elevador da Terra para a Lua, por até metade do caminho, pelo que eu vi, uma aplicação também para esse tipo de satélite como um pêndulo seria para o estudo da mesosfera, porque eles dizem que na mesosfera é muito alto para um balão, porque ele não vai ficar parado nessa região, e ele é muito baixo para um satélite, ele também não vai ter estabilidade para ficar nessa região. Então, se você bota um satélite mais acima e desce como um pêndulo até essa região, vai dar para fazer um estudo nesse local, né? Então, uma aplicação de um pêndulo que estica no espaço seria para fazer um estudo desse tipo aí na mesosfera aqui da Terra. E, basicamente, a apresentação é isso, né? Então, tem aqui umas referências. A gente conseguiu publicar esse trabalho numa revista esse ano. O trabalho de Borov, German e Kosenko é esse aqui, 2012. O trabalho que deu a ideia de sair simplificando tudo para só usar um valor de beta, tanto positivo como negativo, foi esse trabalho de Kolostov. E aqui a referência do Markev, que é onde tem os métodos das construções das curvas. Então, é isso. Agradeço aí a atenção.
Ok, então aqui o Laudelino. Is there any question? Questions or comments?
Sorry, not speak English. Professor.
Oi.
Opa,
Eu ou Hildeberto?
todos dois. É o seguinte, nesse problema, eu estava falando com o pessoal de trabalho aqui na Universidade Federal de Sergipe, que trabalha com um pouco de robótica. Aí, se esse problema, porque é um pêndulo, se for com pêndulo duplo, é como se ele tivesse um braço, fosse um braço que fosse pegar um objeto em órbita e resgatar, né? Já se você fosse pegar múltiplo, né, fosse um pêndulo múltiplo, né, e você tendesse a infinito, então ele seria como se fosse uma mangueira ligado, onde o corpo seria por exemplo, poderia ser um astronauta, né, pegando um objeto em um determinado ambiente, em órbita, né, no satélite da Lua ou em Marte, pegando um objeto e trazendo para a espaçonave, né? Aí, se isso é um problema pertinente, ou se tu vê alguma coisa, Laudelino, porque já sendo com pêndulo duplo, é bem complicado fazer o estudo analítico. Imagine se for com múltiplo pêndulo, né? Com múltiplas hastes, e fazendo essas hastes tender praticamente a uma curva suave, né? Praticamente, né? Como se fosse uma mangueira, né? Se isso é um problema válido, né? Porque quando eu me lembro que você fala da sua terra, foi no primeiro momento eu pensei nisso, e depois no pêndulo
Mas
duplo.
isso é complicado de fazer, pegar várias articulações e fazer tender ao infinito. Tem um amigo meu que é físico, ele tinha mencionado isso, que seria a forma de, como é que se diz? Se aproximar de uma corda, né? Mas é complicado, né? Eu acho que ficaria muito delta, ou muito teto, né? Muito ângulo para analisar.
Mas se poderia ser estudado de outra forma, Laudelino, professor, se eu teria um pensamento, alguma coisa.
Esse problema é conhecido como multi-body problem. E o problema no caso de uma corda, é o tether. Tem muito trabalho nisso e tem interesse tecnológico e tal, mas são problemas bem mais complicados do que esse analisado por um pêndulo simples que o Laudelino fez. Mas, é claro, é um trabalho importante, é um assunto importante e é muito pesquisado.
A gente chegou a fazer um agora, até Gerson me ajudou, né? Tá tentando aí o do pêndulo duplo. Mas até agora não publicamos.
Any other question?
O tether é títere, né? Em português, né?
Como?
O tether é títere, né?
É títere?
Títere? Eu sempre perguntei qual seria a tradução.
Só observação.
Bom, não havendo mais perguntas, vamos... no more question, let's start the speaker again.
Hildeberto?
Yes?
No, sorry.
Agradeço.
Okay.
Thank you.
We have your video.
Huh?
Happy birthday, Hildeberto video.
Shall we start?
Mais linda, mais cheia de graça, é ela, a menina que vem e passa, um doce balanço caminho do mar. Moça do corpo dourado, do sol de Ipanema, o céu balançado é mais que um poema.
Happy 80th birthday, dear Hildeberto, and many more birthdays to come. I remember meeting you in Mexico City at the airport in 1991, when a group of us tried to figure out how to get to the first HEMSIS meeting, which was held in Guanajuato. So I remember there was a special bus, but we didn't know how to find it. With the Portuguese, we managed to communicate with some Spanish people and figured out what we had to do. 2 years later, he invited me to come to Brasilia to give lectures on computer algebra during the summer school. I enjoyed very much your hospitality and generosity during that visit and the many visits which followed. Most of my visits to Brazil were to Recife, but you also invited me to come to Aracaju, Rio, and São Luís, among other places. Always enjoyed talking to you about our common interest in celestial mechanics and to work on some joint projects. I'm sad that we couldn't get together this year, but I hope that we can do that in the near future again. Until then, stay healthy and all the best to you and your family. Again, happy birthday also from Roberta.
Thank you.
So just to say that I put the link to the article in the chat. I think it is open to everybody. I think regular and chaotic dynamics let it free for everybody. Only this.
Shall we proceed?
Siga com os trabalhos.
Yeah, now, yeah.
Okay, now we come to the second speaker of the day, Donald Saari from Northwestern University, University of California. I would like to say a few words about. I met Don Saari about 40 years ago in a conference in São Paulo, and there I invited him to come to visit Recife, and he came here for a month and gave an excellent course in celestial mechanics, and he was the first of a series of visitors to the department. He came other times, and all these people helped to consolidate the group of celestial mechanics in Recife, and we are very grateful for his collaboration. So now we have Don Saari speaking on the controversial theme of existence of the non-existing black matter. So he's going to talk visiting the dark matter controversy by using celestial mechanics. Please, Don.
Thank you. Let's see. So if I can get this up. Yeah. Go to share. Okay. Yeah. I'm going to talk on one of my favorite topics recently, which is the issue of dark matter. And looking at it from the perspective of celestial mechanics. A couple of you have heard the first parts of this, but there's some new stuff towards the end here. But let's get started on the most important thing. First of all, happy birthday, Hildeberto. You know what? We both made it to 80. I'm about 6 months older than you. You know, the kids that are out there, you know, the ones that are only about 50 or 60 or maybe even 70, they think that 80 seems old, but we both know that, hey, I can do anything I could do when I was much younger, like 78 or something like that. But yeah, 80's there. I can't wait till this damn pandemic is over so we can get together and have a drink together and get caught up on everything. Now, a lot of happy memories. As you already mentioned about being in Recife, I have a couple of times down there and had a lot of fun and really enjoyed it. And also enjoyed having you and your family up here at Northwestern for a year. Now, let me explain to people about what Recife and Northwestern. Now, in the places where I was in Boa Viagem, the temperature was always 27, 28, 29 Celsius every single day, you know, or low 80s, high 70s, low 80s. When Hildeberto came to Northwestern, well, there's a little bit of a temperature change, right, Hildeberto? Remember that? What happens is in the summer it was over 104, over 40 Celsius, and in the winter they had that wind chill factor that one day in February where it was in Celsius about minus 50 or so. And so in that 1 year that Hildeberto was at Northwestern, the temperature differential was 90 degrees Celsius. Whoa, quite a bit. Now, let me get to the lecture. All of us have heard about the issue of dark matter. A lot of us really don't know what it is. And so in this expository lecture, I'm going to give you a little insights into what it is and how to examine it. And it's highly appropriate for this lecture because some of the tools that I'll be using were developed during my visit in the early 1980s to Recife. It all starts with Kepler's third law. Now, we know what a genius, what a very bright man. Just by looking at data, what he was able to do is come up with his three laws. The first two said that rather than motion going in an ellipse, a circle rather, it went in an ellipse. And if it's going in an ellipse, then the issue is it can't be going uniformly. And so how fast is it going? And so his first two laws said it was an ellipse and what it did, how fast it was moving along that ellipse. But the third law really was a difficult one. Remember, what he had to do is he had to try to pull together all of the planets and try to show what was the relationship between their elliptic motion. I mean, look, Mercury going about 32 miles per second going around there. And take a look at the differences of the speeds. Earth going about 18.5 miles per second. Now, when I grew up, there was the story of Superman going faster than a speeding bullet. Well, a speeding bullet goes about a half a mile per second. And so the Earth going around the sun is going about 37 times faster than the speeding bullet. And look at that. How in the world are you going to make head or tails out of all of that and try to show all the planets are related to each other? And that was his third law, where he brought together about the period of revolution and the size of the semi-major axis. Now, for today's lecture, of the importance is the downward swoop. I mean, you know, that third law, I mean, the planets and everything is going down like this because you're farther out, the semi-major axis is going to be quite large, and so therefore the period of revolution is going to be very slow. On to Newton. Now, the question, we all know Newton's laws. This is a group of celestial people in celestial mechanics. We all know Newton's laws. So the issue is, how can we use it to determine the mass of the sun? Well, let's see. The planets are all pretty darn small with respect to the sun. So for any planet, it's really, first approximation, it's a two-body problem. It's the sun and the planet's in a circular orbit. So here we have Newton's equations in scalar form, in the radial form. And so I have the inverse square force law and then terms from the rotational effect to get the scalar form. It's a circular orbit. Being a circular orbit, the radial acceleration is 0. Now I can divide out the mass of the planet, and I have a simple algebraic equation that you can and I have taught to freshman calculus students about how to find the mass of the sun. And the mass of the sun, just solving for that, is this expression right here. Here's the problem. The mass of the sun depends on which planet I'm talking about. So we have a problem. We can figure out the mass of the sun by looking at Mercury, looking at Earth, looking at Venus, looking at Mars, looking at Saturn. What if the mass of the sun changed with the planet? That would raise serious doubts about Newton's equations. But no problem, because that is the relationship between RV squared is given by what? It's given by Newton's, Kepler's third law. In other words, what happens is this circular orbit, or rather this expression right here, is really Kepler's third law for circular orbits. Now, let's go to the fact if I had a smaller mass. If I had a smaller mass, then we go up to the equations up at the top. If the mass is smaller than the expression right here, then what happens is the acceleration is going to be positive, not 0. And that means that we will have a dissipation effect. It's going to start moving off. That's going to play a role in what I'm going to talk about when I get to dark matter. Now let's move on to the next intellectual giant in this story. That's going to be Vera Rubin. I regret not having a chance to meet her, but anyway, her son, his office was next to mine over here in the math department at UCI. Now, to describe her contributions, let's go away from the mass of the sun to ask, what is the mass of a galaxy? Now, to find the mass of the galaxy, you would need to solve the billion body problem. Well, I guess us mathematicians have been a little slow. We're still working on the 3-body problem. And we haven't got to the billion body problem. And so what the astronomers have to do is they have to make an approximation. What they do is they replace Newton's laws with a continuum approximation. Then, with some cleverness, they show that the mass of a galaxy out to distance r is given by this expression right here. In other words, r is the distance of a star from the center of mass of a galaxy. The rotation velocity is how fast it's spinning around the center of the galaxy. And of course, we have the gravitational constant. So this is the equation that's been used for, I don't know, long time. I think Oort used it in 1920s when he was looking at the mass of the Milky Way and things. So here's what Rubin did. What she did is with this machine that you see her looking at right here, she found had a new way of trying to find the rotational velocities of stars in a galaxy. And this is what she found. Notice what this looks like. In every one of these galaxies, the rotational velocity starts going up in an almost linear fashion. And then what it does is it ends up being essentially horizontal, all of them. Well, this caused some problems. People didn't believe that could be possibly true. And because what they all expected was this Keplerian dip, like we have in Kepler's third law. But we don't have that. And what happens is that if we look at the masses, the known masses, we would have that Keplerian, and looking at this equation up here, we would have that dip. But we don't have the Keplerian dip. And take a look what the rotational velocity is. The rotational velocity then is essentially a constant. If it's essentially a constant, that goes up to this equation on trying to find the mass, and it says that the mass has to grow asymptotically, like a constant times the distance from the center of the galaxy. Well, there's a problem here. The problem is there's not enough known mass to satisfy that expression. And so that's exactly why we come up with the dark matter problem. The source of dark matter, it says, well, hey, come on. If we don't have that the right amount of mass, then what happens is the mass of a galaxy is too small. As I showed you in the previous slides, that means that stars are going to start shooting off. They're not going to be in circular orbits. They're going to start moving off. And that means that a galaxy is going to dissipate. So the source of dark matter then is, it's equal to the predicted amount from that equation you see up there. Well, they have other equations, but they're all essentially the same, minus the observed. Now take a look. Take a look at that Keplerian swoop. What happens is where that red line is, I go a little bit to the right there. And what do we have? We have that the largest difference between predicted and observed is out at the edges of a galaxy. So that's why we have a belief that the galaxy is surrounded by a halo. That there's a big, massive halo of dark matter around the spiral galaxies. Okay, that is really where dark matter comes from. That is Rubin's wonderful work. I really was disappointed she never got a Nobel Prize for it because it changed. It absolutely changed our understanding of galactic astronomy. Now here's where celestial mechanics enters. First, look at these two equations. There's the mass of the sun. I derived that for you a little bit earlier. And here's the mass of a galaxy, a billion body problem. Notice they're the same. Now, any of us who have worked in the celestial mechanics, worked on the two-body problem and the three-body problem, we know that if you have an equation, you know, for a multi-body problem, that if the equation looks like it's the same, there's something wrong. So that's what caught me sitting here. How in the world could we have the equation for the mass of the galaxy be essentially the same as the mass of what we have for a two-body problem? I couldn't believe it. So I started looking at it. And he said that, well, look, when you derive the mass, this equation right here, when you derive the equation for the mass of the galaxy, what you're essentially doing is you're saying that it's a two-body problem. That isn't the way they derived it, but that's what it breaks down to. One of the bodies is all of the particles that are closer to the center of the galaxy. And the second body is the star. But we know that's not how n-body problems work. If there's another particle nearby, it's just like being in love. You're not interested in each other. You're getting close to each other. You're not interested in anything else. And so really what happens is with the dynamics of an n-body problem, yeah, we're going to have an influence of all the stars and all the mass towards the center. But we're also going to have a strong pulling effect of nearby stars that are going faster. If you have this pulling effect of stars that are going faster, what must we expect? Well, we must expect that after a while, the velocities are going to start being pretty much the same, the rotational velocities. And that will give you a horizontal line. And in fact, this pulling effect here looks like what we see in the arms of galaxies. It looks sure like a lot of the stars are, and those arms, like some of the stars are pulling the others along. So rather than a star just being a two-body interaction, you know, where one of the bodies is all of the mass closer to the center of the galaxy, both pictures indicate that there is a pulling effect. There's a gravitational effect and there is a pulling effect. How do we measure pulling effects in celestial mechanics? Angular momentum. So really what happens is, my belief was that the equation for finding the mass of a galaxy has to include both the size of the galaxy, you know, the inside mass, but also the angular momentum effects, the pulling effects. And what happens is the first step to prove this statement is I had to find an analytic solution for a billion body problem. And I had to show that the equation, that the expression does not hold. All righty. And where is the tugging and the associated angular momentum the strongest? Central configurations. So I had to create a billion or so body central configuration. Well, remember what a central configuration is. Very, very special. It's where the acceleration vector lines up with the position vector relative to the center of mass. And lambda there just is a substitute for the total gravitational attraction. But the central configurations are much more than that. It says that all of the lambdas are equal. Well, actually, creating such a device is quite easy. 10 to the 10th, 10 to the 5th lines here. You put them equal distance apart. Then at an equal distance from the center of mass, we'll start off by putting masses of the same equal masses, so they're equal distance all the way around here. A little later on, I'm going to put them a little bit farther out and then a little bit farther out, etc. Well, let's see about that first circle. That first circle is obviously a central configuration. It's Maxwell's central configuration that he used for the rings of Saturn. And by symmetry, they're all pointing in. Now suppose I have two rings. So I have all of these right here, and then I'm going to put masses over here, equal masses all the way over here. Not the same as the ones here, they can be different. Now, what I have to do is if I go back up to this equation, I have lambda 1 and lambda 2, and I have to show that lambda 1 minus lambda 2 is equal to 0 to get a central configuration. Well, let's see. If I put the particles too close to each other, bodies on the second ring are pulling the bodies of the first ring outwards. So therefore, the lambda 1s will be positive because the positions are going outwards. It's pointing outwards, the acceleration. The acceleration on the second ring are all negative. So lambda 1 minus lambda 2 is positive. If I put that second ring too far out, well, the first ring doesn't even notice the second ring. And so there all the lambdas are pointing inwards. And the lambda 2s are very, very small. And so lambda 1 minus lambda 2 now is negative. Nothing more than intermediate value theorem. At somewhere between the two, there has to be a place where the lambda 1 minus lambda 2 is 0. And so therefore, we know that this is going to be a central configuration. And now we just continue in this manner, adding more and more rings. You can prove the existence. Well, how would you prove the existence? What's the central intermediate value theorem in higher dimensions is really a fixed point type theorem. So you could use fixed point type theorems with the arguments pretty much like I just got through giving you. Or you could use Moulton's approach where he gave the collinear approach, or you could use analysis. There's all sorts of ways. So I can have now as many lines as I would like equally spaced. Choose masses, and then I just put the masses equal distance, or not equal distance, equal for each circle on the circles around each of these. So if I have, 10 to the 4th lines, and I have 10 to the 4th masses, I have 2 times 10 to the 8th body problem, and for this central configuration. Now to get an analytic solution, all I have to do is put that into a rotation. And this defines the ultimate of tugging. Placing it into a central, into a circular motion, I get an analytic solution of the billion body problem. Well, that's a rigid body rotation. And so a rigid body rotation, a rotational velocity is equal to the distance from the center of mass. A multiple times the distance from the center of mass. And so now if I go back to this equation, mr, and I substitute that in there, what do I get? I get that the mass grows like a constant times r cubed. There's something wrong here. I didn't tell you what the masses were. And yet the expression tells me what the masses have to be. That's not right. In fact, I can create, just go to a calculus book, I can find as many solutions as you would like. Just find the masses, and then with the series type things, you can find out what will be the total mass, and then you use this expression here to find out how far they're off, and you see that this expression is exponentially off. It exponentially exaggerates the amount of mass. This expression says that there should be a big, big halo around my configuration, but there's not. And so, and the problem is that the angular momentum is missing. So and the next step was to indicate how to include the angular momentum into the analysis. And what I have here is true for any force law, not just the inverse square force law, it's for any force law. Now, this goes back to Recife, back in the early 80s. I remember Hildeberto, we were talking, I gave a couple of lectures on this right here as I was developing it, and that is the velocity decomposition. Here I'm going to describe it in terms of a 3-body problem that works for the n-body problem. And I'm going to describe it in terms of coplanar. It works for 3 dimensions, 4 dimensions, whatever you want, visible space. There's a 3-body problem. And here are the velocities. Now the issue is, what does that look like? Well, look, what can we say about the impact of the velocities on the system? Well, we see that it's moving the system in a counterclockwise direction. But how will the shape of that configuration change? Well, I'm going to do this only for the rotation term. Everything I say also holds for the radial term. Now, let's compute. Now, if you have this information here, the angular momentum C can be computed. I know the velocities, I know the masses, I know the distances. And this will play a role in a few seconds, because what happens is I first want to find what should be each body's rotational velocity so that the configuration remains unchanged. And this is just a calculus problem. We just rotate each body around the z-axis with a spin value of s. And we know from undergraduate undergraduate physics what is the spin value. Let's look at this angular, this moment inner product right up here. This is a natural inner product for the n-body problem, because I incorporate the masses and what happens for each of the body. For example, if R is the listing of all of the radius vectors, then the moment of inertia is, polar moment of inertia is just R squared. And we now know from just undergraduate calculus or physics that S is equal to C over R squared. So we know the value of S, the spin value. So now I can find what they are. What I'm going to do is, when I designed this problem, I designed it so S was going to equal 1. So therefore, that the spin, what should be each body's rotational velocity, so the configuration remains unchanged, is just going to be essentially the distance of the radius vector. That's obvious. That's simple. Now I want to find the rotational velocity vector that changes the shape of the object. This is simple too. All I'm going to do is say, well, I got the rotational velocity, and let's subtract off the green arrow. So what happens is, let's look here at the one in the lower right-hand corner. I just take that red arrow and I just project it down so that I can find its rotational velocity. And then I subtract off the green arrow, and I get this little, what's left over. If I go up to the second body, well, let's see, the green arrow is larger than the red arrow. And then over here, I have this right here. So now we see what's going to happen to the shape of the configuration. What happens is, two of the bodies are moving, in, as far as shape is concerned, they're changing in a clockwise direction, not counterclockwise. One of them is moving in a counterclockwise direction. So we see that the two bodies on the right are coming closer together, which is not entirely obvious. And the one on the left is shooting upwards. So we can see what is going to be the shape of the configuration. The theorem, which is of importance, is that the green and the blue arrows vectors are orthogonal. And here is the expression for the orthogonality for the n-body problem. Now, let me explain what this is. The first term, mass, that's obvious. The second term, R, that's obvious, that's the radius. The third term, well, that is right there, is the magnitude, the sign magnitude of the blue arrow. So by sign, I mean that if it's the system is moving by the green arrows, the system's moving in a counterclockwise direction. So if the blue arrow is moving in the counterclockwise direction, then it's going to be the magnitude of positive value of the, if it's moving in the clockwise direction, then the magnitude will be negative. Okay, and so that is a powerful expression. It's powerful because what does it do is it gives you an expression of the mass distribution with respect to the rotation. Now let's go to the galaxy rotation problem and the dark matter problem again. And I'm going to use that expression coming up. The galaxy rotation problem is the following. The solid line is what we observe, what Rubin was the first to observe, and then her co-authors. The dashed line is what should be the galaxy rotation problem, if indeed this expression right here were correct, and we were using only masses that we could observe. So the dashed line is what we should expect to have for the observed mass. And the solid line is what we get from the observations. And the question is, can we explain that solid line without using dark matter? And the answer is yes. What happens is we just have to spin that object fast enough. I mean, it's much like this young girl, my granddaughter, by the way, spinning a ribbon in a morning in Finland. That if it spins fast enough, then what happens is that the rotational velocity curve is justified. And in fact, you can show quite easily that if you take the masses that are observed, the distances which are observed, and the rotational velocity of the solid line, you can find the spin value, which will support that rotational velocity curve. Because I can compute with this information from this curve, I can compute the moment of inertia. I can compute the angular momentum. So I can compute the spin that will support the rotational velocity curve. All right. But that doesn't explain the dashed line. Maybe I can find the spin from observational evidence. That'll give me the solid line, but why can't it also be the dashed line? Well, that's where that equation comes in. And here I'm going to just throw in a couple of new terms. See this line I just dashed in there? That line right there, I call the angular momentum line. It's just SR. And now what happens is you see the red vector. We already know what the red vector is. That's the rotational velocity at a distance. You just go up to the rotational velocity curve. The green line, that's just what we had earlier. It's just going to be the for the angular momentum for the spin. How much does the velocity have to spin to keep a fixed configuration? And then we have the blue line, which is a difference between the two. Notice to the right, the blue line is going downwards, it's negative. To the left, the blue line is positive. It's going upwards. It's the distance between the angular momentum line and the rotational velocity curve. And so what this does then, this curve does, and this dynamics, simple dynamics, what it does is it shows us how the angular momentum and the rotational velocity are tied together. Now we have this mass equation. And remember what this rotation, this W was. This is the blue lines. Some of them are positive. Some of the blue magnitudes are negative. So I can get the negatives on one side, the positives on the other. And what I do is I have an expression. First expression is, let's find the mass times the radius times the magnitude for the positive ones. Now let's find, for the negative, let's find the mass times the radius times the magnitude for the downward ones. And the two have to equal. It's just simple. Now what we have is an explanation. Take a look at this picture. If these two equations right here are equal, then what happens is, take a look over here. What's R? R is very small. What's the size of that blue vector? Very small. So on the left, all of the terms are very small. And so therefore, for these expressions to be equal, what happens is the masses have to be very large. So the masses near the center of mass have to be very large. Now let's go out a little farther. Here, the distances on to the right, the distances are very large. Our distance is very large, and the distance to the angular momentum line is very large. And so therefore, these two terms right here, r times the magnitude of the blue vectors is very large. That means the masses have to be very, very small. And from this expression, you have that if indeed the rotational velocity curve is what you see right there, and the spin is what you get from that angular momentum line, you can show that the masses really are decreasing. They're decreasing. There's no dark matter, it's decreasing, like 1 over r squared, r cubed. Now, okay, that's fine. So we can justify that indeed that the rotational velocity curve can occur with smaller masses. And in fact, when we throw them in the angular momentum in the way that I've stated here, that the masses have to be much smaller as we go out further into the rotational velocity curve. Not dark matter, they have to be smaller masses. Now what happens is, but what about that dash line? Could that dash line also be there? And the answer is no. For a given S, that's defined by the observed values, by the observed values of masses, by the rotational velocity curve, it's impossible to have another rotational curve that is strictly smaller in certain regions. So it's impossible to have that dash line. And how did I prove that? I proved it just by use of this theorem right here. Very, very simple proof. So what do we have? We have that what's causing problems in the dark matter. It's that is that the angular momentum is not being used. Is that they're just using a two-body approximation. That they're ignoring the tugging effect. That when you throw in the tugging effect, you're throwing in angular momentum. And when you're throwing in angular momentum, then what happens is you get a completely different explanation. And so, so that's my take on dark matter and the dark matter problem. And so what's the final message? I have two final messages. The first one is that the area of celestial mechanics, we have a lot to offer for concerns coming from astronomy. The trouble is we don't look for it. We primarily look at issues that come strictly from celestial mechanics. But we have to start looking at some of these issues. There's a lot of good books out there where you can see where they're making approximations. And you can say, whoa, I'm not so sure that's true. A lot out there. And the real final message is, happy birthday, Hildeberto.
Let's thank the speaker. Questions and comments?
One of the delights of this conference, Zoom conference, or what? Not Zoom. It's whatever it is. Google Meet. There we go. Is to see friends I haven't seen for a long time. A true delight. And I enjoyed looking at. Like I haven't seen Dieter. I haven't seen you in at least 15 years. So it's a lot of fun.
Questions?
I guess it was too dark.
Okay, well,
I want to say, yes, I want to say excellent talk. I really enjoyed it because also I'm not a believer of the dark matter. Do you have anything written down about this? Because I've seen
Send me an email.
Yes, I'll send you an email. I've seen before an article by the group of Milano, and they get to but I haven't seen the detail. I can send you the article. They get also to the fact that the matter is distributed not uniformly, like you said. They get that if you rearrange the matter and so on, you don't need to get to any dark matter. So I think that is a group of Galgani in Luigi Galgani in Milano. But I would really enjoy to see what you wrote because really inspiring. Thank you for the excellent talk.
Well, thank you. Thank you very much. What happens is send me an email. I've been working on this a long time. You know, one of the people I want to credit in some of this is encouraging me when I started working on this, more than 10 years ago, is Ken Meyer. Ken, what he did is he gave me a lot of encouraging type comments. I mean, I've been talking about this for more than a decade now, so I got a lot written on it. But Ken was one of my early supporters, and he was called the dean on the first lectures in this series. He was called the dean of celestial mechanics. Ken, I think that means that you're the old fart.
Hi there. I have a question. Have you any reaction by astrophysicists or physicists about your model?
Yeah, I have quite a bit. What happens is the astrophysicists and astronomers who have heard my lecture, I've given lectures on this in a large number, as you're well aware, in a large number of places. The astronomers and physicists that hear it agree with it. Those that are getting funding for dark matter do not agree with it. But they don't have an argument against it. I had one of them who ended up being a referee for one of my papers, and I had to go publish it elsewhere. And he said that, well, if you do such and such and such and such and such and such, I'll accept it. So I did all of them. And then he said, well, what you have is correct, but, well, it's too technical. So
another question is it reasonable not to take into account general relativity in this problem?
Well, see, that's an interesting question. What happens is that relativity is not used at all when they're talking about dark matter. The velocities are not high enough. Now, what happens though is if you take a look at that curve, that rotational velocity curve that I started with, they make an assumption that Newton's law holds. Well, they haven't validated the fact that Newton's law holds for, what, 200,000 light years. In fact, Milgram from Israel said that if we slightly modify Newton's laws, so that we have another term that you just won't see in close, you know, like a 1 over r cubed type term instead of 1 over r squared. It won't show up at all in small distances, but in large distances it will. And so he shows that by using arguments of this type, that he can explain the rotational velocity curve without dark matter. And so there's papers out there of that type, but they're not, the astrophysicists, for the most part, don't accept it. But again, in answer to your question, yeah, a lot of the astronomers and astrophysicists that aren't working in dark matter do accept it. I gave a lecture in New York, and I was introduced by an astrophysicist, and at the end of the lecture, he says that he bought into it.
Thanks.
Nice seeing you again, Ellen. I haven't seen you in, what, 15 years. Hildeberto, I can't hear you.
Your microphone, Hildeberto. I close it.
Can you hear me? Can you hear now?
Yeah.
Okay. Can the inverse square law be modified to explain some of these? Instead of the potential being inverse square, the law is just the inverse of the distance.
Yeah, well, inverse force law will not work on there. But if you take a look at my argument, and this is why I made the comment a bit earlier in there, I said that the argument that I have there for the velocity decomposition and getting to the angular momentum, I stated that it holds for any force law. So it'll hold for relativity, Alan, if you want to say that maybe relativity causes that force law. The angular momentum will still play a role, and the same role that I showed in here. And Milgram's argument with 1 over r squared, then with a 1 over r cubed type perturbation type term, the argument still holds there too.
Mm-hmm.
And so, in fact, I was absolutely delighted when I discovered that indeed discovered. I mean, it isn't hard to discover, but it took me a while to realize that the argument holds for any force law. It just means that the force law is manifested by the shape of the rotation velocity curve, and still everything else goes through.
Okay. Any more questions? Okay, let's look at the speaker again. Anete? Anete? Anete?
Sim, professor.
Alô, Anete?
Tô ouvindo, tá ouvindo?
Ok.